Cryptography is the reason your personal photos stay securely on your phone. It's the reason no one can access your credit card info. And it's the same reason the raunchy texts you send to your ex are hidden from the rest of the world. But now, all of that could be uncovered thanks to quantum computers that can cause mayhem in cryptographic key management. But there's good news. All of this could be stopped if and only if cryptographic key management stays on pace with computing power. So watch till the end to find out how this could all happen. Imagine you're running a secret club and you need a way to let the members communicate securely without anyone else finding out what you're saying. To do this, you give each member a special key that can lock and unlock messages. This whole process of handling the keys, making them, giving them out, keeping them safe, and ensuring they don't fall into the wrong hands is cryptographic key management. But instead of a secret club, it's every piece of information on your computer. So cryptographic key management is the process of creating the keys, giving the keys to different people, keeping those keys safe, using the keys, renewing or updating the keys, and when some get too old, destroying the keys. So, in essence, effective cryptographic key management ensures that only people that you've authorized with a key can access the secret messages, just like your club's system keeps secrets safe. But the tech world is changing every single day, and we need better cryptographic key management systems than ever before, especially since quantum computers and AI have been making major advancements in recent months. As technology evolves, so will our need to smash that like button, just like you should if you haven't done so already. But no, in all seriousness, as technology evolves, so will our need for better cryptographic key management. If this doesn't happen, it could create many problems for major organizations and individuals, from unauthorized access to data breaches, to personal or financial data, to even increased vulnerability to hacker attacks. And everyone who uses cryptographic key management, which is basically everyone, will all be in danger. So far, cryptographic key management has been evolving at the same pace as technology. But will that be the case in the future? In the past, these keys were created manually. We're talking about the early days before computers took over. Think of it this way: if you decided to write a letter, but instead of letters, you use numbers, the cryptographic key in this case would be the number system that you would need to decode the letter. If you told what you did to your best friend, then he could easily read the letter. But if it was someone who didn't have this key, then they would only see a bunch of numbers on a sheet of paper. That's the most basic level cryptographic keys. When computers were introduced, things began changing rapidly, and cryptographic keys were instantly automated. Computers started generating cryptographic keys using mathematical algorithms, ensuring higher randomness and security. Techniques like public key infrastructure began emerging, enabling secure distribution without physical exchange. Back then, systems were centralized, and single points of failure, e.g., servers storing keys, were common. After that, in the 70s and 80s, public key cryptography introduced the concept of asymmetric keys, one public and one private, revolutionizing key management. The need to physically exchange keys was gone for good, and so did the risk of intercepting these keys. However, back then, computing power was very limited, which caused problems for these systems. That problem was overcome with the rise of large-scale networks in the 90s and early 2000s. It was common for companies to use PKI for managing keys in large networks like the internet. Certificates and trust chains allowed scalable management for thousands or millions of keys, and they began creating special hardware devices to store and protect keys securely. But this created a different problem. Now they need complex implementations and constant monitoring against emerging threats. That's why in the 2010s, with the advent of cloud computing, key management as a service became a thing. Cloud providers like Amazon Web Services, Azure, and Google Cloud started offering scalable key management solutions. The keys could now be rotated and updated automatically to reduce risks of compromise. That being said, the problem this created was trusting third parties with key management and ensuring they would comply with regulations. This brings us to today, the zero trust security models, AI-driven key management, and even quantum-resistant cryptography. Because third parties now manage the cryptographic keys, there's an emphasis on the principle that no system or user is inherently trusted, requiring more sophisticated key management, which gave birth to zero trust security models. Crypto did its thing with blockchain technology, which created decentralized key management. In other words, some companies use blockchain and distributed ledger technologies to explore decentralized ways to manage keys securely. Near the end of 2022, and to this day, AI key management has slowly become a thing. Artificial intelligence is being used to monitor, analyze, and optimize key usage in real time. And since major companies began working on quantum technology, which will break traditional encryption algorithms, the priority is creating quantum-resistant cryptography. Imagine you have a super secure vault to protect your most valuable secrets. Right now, it's locked with an ultra-complex combination lock that no one can crack with normal tools. But you hear that a new kind of super tool is being invented that could easily pick your lock in seconds. You realize you need a new type of lock, one that even this futuristic tool cannot break. This is the idea behind quantum-resistant cryptography. You see, today's encryption methods like RSA or ECC are based on problems that are incredibly hard for regular computers to solve. These locks are effective against current tools. But recently, Google's new Willow quantum chip solved an equation in 5 minutes. If you were to give that same technology to the world's fastest supercomputer, it would need quintillions of years. Quantum computers can solve certain types of problems exponentially faster than classical computers. For example, they can use Shor's algorithm. This quantum computer can quickly break RSA or ECC encryption. When this super tool becomes widely available, many current encryption systems will no longer be secure. That's why we need to invent new ways of cryptographic key management that would be able to deal with quantum computers. Quantum-resistant or post-quantum cryptography is like designing a new type of lock that quantum computers can't pick. These systems are based on mathematical problems that are hard for both classical and quantum computers to solve. In simple terms, there are basically two types of encryptions that are hard even for quantum computers to solve. The first is lattice-based cryptography, which is like finding a needle in a high-dimensional haystack, and hash-based cryptography, which relies on the difficulty of creating collisions in cryptographic hashes. But what can we learn from the past about how to create better cryptographic key management? Whatever we do, we cannot store the encryption keys in the same location as the encrypted data like Sony did in 2014, when hackers breached Sony Pictures and found unencrypted files containing passwords and encryption keys. This allowed them to access sensitive data easily. In a similar fashion, in 2011, DigiNotar, a certificate authority, failed to revoke compromised certificates after a breach. Attackers used these certificates to impersonate websites, compromising user trust. This is why we need to implement key rotation policies and immediately revoke compromised keys to maintain security in future encryption technologies. Or in 2008, when the Debian Linux project accidentally introduced a bug that made open SSL keys predictable. Keys generated during this period were easy to crack, and it caused a plethora of problems for everyone. This is why we must use robust key generation algorithms with sufficient entropy and validate cryptographic libraries before deployment. So, in the future, a system like QKD or quantum key distribution system might be used to store things safely. QKD uses the principles of quantum mechanics to securely distribute encryption keys. It relies on quantum states like photons to ensure that any eavesdropping attempt will disturb the system and be detectable. They could be integrated into global communication networks, including satellite-based QKD systems for secure key exchange over long distances. So, communications between governments and securing financial transactions could be made using QKD. Do you know any other cryptographic key management systems that would be used in the future? Here's another video AI enthusiasts loved watching. This is AI Exposed, demystifying the world of artificial intelligence, one video at a time.